Hey everyone, in this video we're gonna use Python script in simple steps, show how to visualize these network graphs and calculate network metrics that are built from your usual transaction tables that you see in bottom right. Right, the data that you see are a set of transactions from invoices in different dates, different buyers and sellers, and each of those buyers and sellers have their own set of features. Now, one important features of the many different type of data, including transaction data here, is the relation that the elements or agents in the data have with each other. Who interact with who trade with whom are very important. So we're going to focus on that and see what we can learn by visualizing and calculating those metrics. So in specific, we're going to do in this video compute three things, which is economically very important and we usually care about them. First, who is systematically important in trade or in the data, who is more central, who is bearing the most in intermediation, who is most likely to be brokering different deals, different connecting different part of the network or buyers or sellers, and also mostly looking at buyers. We're going to see who from the buyer are more dependent on seller, limited number of sellers, so possibly they are more exposed to supplier and supply chain shocks. So we're going to apply some non-network concentration metrics in a network context, which would be interesting to see how the mix. Then we're going to do a, define a different network, which is not necessarily buyer seller, it's buyer buyer, and it's projected buyer buyer network when relations are defined by how similar buyers are in terms of their choice of partners, in terms trading partners, the sellers from whom they purchase different goods. And that's actually what you see here. There are different buyers that are clustered in different communities by one of the other things that we're going to show in this implementation guide tutorial in different steps, and different colors shows different buyers that are mostly similar, and that similarity mainly comes from the choice of trading partners, but also it could come from the other features that they have. So applying sort of clustering in the context of network. So let's jump to the code to see how we can do this. First of all, before jumping into the code itself, I have to say there is a part one of this video series that focus on the concept and theory and the intuition behind these metrics, which I define in video slides and define the intuition of the betweenness or the centrality and the type of dead networks that we define from a data analysis and from a economics of network perspective. And the link you see in top right, so definitely have a look on that if you're interested to look at on the theoretical side and the definition and intuition behind what we show in this video is mostly code and implementation. So let's jump into the code. So in this project, as I said, we built two networks, buyer-seller transaction, which each link or edge is a trade between buyer and sellers, and we're gonna calculate and sum all different trades that, let's say, on amount of days in our data, we could have many different or transaction between a single buyer or seller, or there could be only one transaction. We're gonna sum it up, so we have one a total trade between them. That's how we're going to do. The second network, as I said, is a buyer similarity network. And we have a config file when we have certain variables that we control about the visualization and some of the calculation that I'm going to show you. So let me zoom in a little bit. We use NumPy for the usual numeric operation and for cosine similarity. So we use cosine similarity to calculate the community detection as similarity, the buyer-buyer similarity in terms of how similar they are based on their trading partners and their supplier or the choice of supply that they had on the portfolio of supply that they had. Pandas for the usual pivoting and essentially where data holds. Most of the time we use data frame. NetworkX is the central one to calculate the centrality type metrics. The betweenness we use, and also the PageRank we use, and NetworkX, which is a very commonly used one. Um, and also the PyVis is the main one that I'm going to focus. This is the one that we're going to use for interactive visualization that you saw in order to have a very nice and with lots of customization options, which you can have in HTML format at the end. And obviously you can take a snapshot from that as well. So the output will be the set of visualization that you saw, but also we're going to have something like this. We're going to have a table where we can identify who are the top brokers, right? For example, this one, we are looking at who are the top brokers based on their betweenness, which is this set of sellers and buyers. So based on how connected they are to other central buyers or sellers, how then you can find the top hubs, which would do that centrality, but top brokers have diverse is their essentially um, choice of buyers or sellers. And top dependency is again is the final calculation for us to identify from buyers who are more concentrated and have less diversity in their choice of supply. So for example, in this example, we have two buyers that their the the metrics that I'm gonna define later on. This is HHI. It's a usual concentration metrics. It's actually one maximum. That means that they have only a choice of one supplier. So we're gonna again. That's one of the final output that gives us a sense. We identify and calculate those three angles. Again, in the accompanied the companion video that I defined these metrics, you can see a little bit more intuition behind them. In this video, I'm gonna talk about them a little bit more as well. So that would be the output, couple of CSV files that gives us the network itself, but also the top brokers, top central players in from different perspective and different visualization that we can have. Now, what do we need in configuration? So this is where actually we define our network. So we use, I'm going to show you quickly how we generate our actually network data, because the first question you might have, can I have a synthetic data to work with? So we're going to show you very briefly how to realistically create transaction data that gives us that platform to work on that. So that is, we use some randomization for that. So that is for that generation. Also, for the other three is we're gonna use two different network data. One where we only look at the month of trade. Another when we look at in the second run, we look at 6 months of trade. So obviously, um, the more you define your data more extensive in terms of time, that will be the type of network that you will see will be different. So that's one of the things to highlight, right? The definition network. What's the data? What's the cutoff that we're going to define on the time in itself? But also number of buyers and sellers. So we define it here. And the rest are for visualization that we have. It's the choice that for the final visualization, we want to have certain threshold in terms of what are the nodes or edges that we want to make it visible or not, which I will gonna show you later on. And here we add those again. We have couple of other, so that's where we define the config JSON that will show you, and we built it in. We call it in here, and then we have couple of other variables here. So the context alpha, again, it's easier for me to, when we get them, to see what they are. But essentially, there are different variables that either help us for visualization, or we're going to help us for the calculation that we're going to get back to them, where in different steps, right? Okay, so the first step on the code itself, and let me be a little bit There you go. So synthetic transaction, right? So that's where we are building our network. So what's going on in this? So let me go through them. So these are buyer and seller come from different regions, different industry, different sizes for each buyer and seller, right? Different categories. So what you see are other features, non-network features that buyer and seller can have, right? So I'm defining them, hard code them, uh, that what they could be. Now the second step is define them, actually what is the rule that this buyer and seller should be with which frequency and with which selection they should be connected to give us transaction in different dates, right? And we're going to do them in two different runs, as I mentioned, which the config file tell us in which intensity. So let me just go through a couple of rules in terms of how we use this synthetic generation of the network. I'm not going to focus them most. Let's have them as given because the biggest thing to focus is actually the visualization. And actually, you may have already your network data where you want to customize and use this format for your own need, right? So, but here again, the synthetic transaction. So we simulate a firm-to-firm economy, right? And as you saw, buyer have different industries, region, and size. Sellers have their own specialties and reliability, and we're going to define them what they are. So the core design is the repetition and specialization, right? So it's the fact that buyers repeatedly transact with preferred sellers, and that preferred sellers comes from some sort of reliability, right? So, and the fact that you are in a specific industry, you may only rely on a set of, you may need a specialty, and suppliers with those specialties are going to be among your choices. So that repetition creates some sort of stickiness. We're creating those stickiness that if with some randomness we have buyer 2 with seller 5, there is more chance that that transaction is going to be repeated. Not always, we have some random, some other choices as well, but that's one of the realistic nature of the transaction data, right? Then later on, so that's what we do essentially here. In the industry category weight, what we're gonna do here is essentially we make the demand category mix depend on the industry, right? So we define industry and say, depending on which industry you are, your demand may come from different specialities, right? So that kind of, again, limit and make the connection between buyers and sellers based on their features more clear. And then we define, we make the entities to buyers and sellers. We add the different features for each of those buyer and sellers, which is, that gives us just buyers and sellers, and that is the main that simulate the transaction. So here is the notion of stickiness and the repeatedness that I mentioned. We define seller reliability, and we define a notion of stickiness that comes from whether you already had a node with that edge with that buyer and seller as well or not, and how similar you are in terms of being in the same region geographically. That's a key, and also um, whether the seller is reliable or not from the reliability that we built in to the network. So there again, that stickiness is one of the biggest thing, and the other thing is distributor effect. That the fact that we had size, right? So one of the a specific feature of this type of data is that large player obviously have more disproportionately a larger size of the network, even more proportionate than there are in terms of their size. So large distributors here cover many categories, and they naturally become hubs, possibly from as we define hubs in different ways. So that's essentially some of the features that we define and use in the data, right? So we define it in different runs by using different seed and different day runs. We get the data here. So if we look at now, um, let us run this. So I just ran this one, and you see that I can look at buyer and sellers and look at the most frequent nodes, the edges that I had. For example, we had 5 transactions between, and it seems that this buyer is going to be one of the hub players in the buyer side because it is active in 2 frequent actually deals here. So the specific identity of transactions that are and trading partners that are repeated here, right? So okay, let's move on to next. Again, that was just something that we needed to have, so I didn't focus on that in each steps because that's let's take that as a given that we have that data. Now next, we aggregate transaction into edges, and each edge is one buyer seller pair, right? So we have the nodes here, which we look at. If I look at the df one, that's what we have. And if I look at the columns that it has for me, it has transaction data, date, buyer, and actually I have it here as well, not this one here. So you have buyer seller data, and there is some buyer related information and some seller related columns, right? So we separate them essentially um, to have the node buyers and node sellers are two sub part of that data frame. And then what we do here, we define the nodes, so then we concatenate them. So we have the buyer sellers in one big long vertical, essentially portion, right? So because this is looking from perspective of node, whether that's buyer or seller, but obviously now we have an additional column name for them, which specify for us whether they are buyer or seller. And now we have node ID instead of buyer seller ID. So that would be our node um, layout of the data. Edge would be um, essentially looking at grouping, right? So what we're gonna do, we're gonna look at any buyer and seller in the data. We have possibility repeated transaction with some of them. So we're gonna add up for any transaction between any two pair of ID, the amount, which is the total amount of sale between them. We sum it up and we have the edge data. So if we run this, then we can look at the edge data. Each unit of transaction is a pair of buyer and seller, source and destination. Source is the seller, destination. You could define it as directed or indirected, on undirected. So I don't care about direction here, but that's something you could do. And also the number of um, trades that they had between them. So we have it there as well. If you look at the nodes data, that is just information of, so we have buyer and seller in one part. Some of them, they have some missing data, which is part of the deal of the usual data anyway. So we simulate that and their features here. Or actually, this is buyer information, so they had to be missing for sellers. Okay, that's actually natural. Let's go to flow metrics. How do we now calculate the metrics and visualize the network itself, right? So here we calculate 3 families of metrics: brokerage, embeddedness, and which is or PageRank, and concentration risk, right? So this is HHI that is usually defined for market concentration is the sum of the share, and each share or S is the share of purchase that I have as a buyer um, distributed among different sellers. Now we define our network here for betweenness, and for betweenness what we do, um, again, in the theoretical counterpart, in the video, I explain more about this, but betweenness centrality essentially count how often a node lies on shortest path, right? So in an economic network, shortest path should prefer strong relation because the strong ties have lower friction, right? So how do we define that the strong ties and lower friction? In betweenness, there is a notion distance, right? That there is. And the higher the distance, the higher the friction and the lower frequency of a trade and node between that two pair of nodes that we're talking about. So um, we can define it indirectly with the concept of the amount that we have here, where is the total amount. So what we do, we define distance 1 over log of distance, essentially. That's how we define it. And the reason we use log to make it more smooth, such that if we have a large amount of weight or amount, it doesn't create essentially discreteness and weird behavior such that the whole um, calculation are concentrated, located among couple of the big deals, so they don't distort the data. But the biggest thing here is just the fact that if there is higher amount of sale between a buyer and seller, we translate this at a lower distance, lower friction. So that's how we define that inverse relation of weight or distance and amount. Right? So that is the key. And again, log, we use it because a spend is heavy tail and we want that diminishing return. So if there is one giant edge that doesn't dominate every shortest path. Just to give you that um, quick intuition. So we have the betweenness centrality here. Again, more explanation in the companion theoretical video that we have. Then we define the PageRank. PageRank, again, we use NetworkX for calculation. What do we do for that though? So we are using an undirected weighted graph here, right? And PageRank in this situation is the fact that you land more often on nodes connected through strong weights, right? But if weights are raw spend, then PageRank can become a size ranking. So we need to be careful about that. And one thing we can do, instead of using raw spend, we use weight. We use standardized weights, right? So essentially, that's why we uh, calculate total amount and we create these weights. We um, making them standardized by creating this fraction that gives you that probability type interpretation for each weight of the link, right? So that's one thing that usually you need. But also we use a symmetric notion. So we convert each edge weight into a symmetric dependence weight. So as you see, uh, we look at, okay, this amount of trade between a buyer and seller, how big it is as a total amount of spend by buyer, right? How much of dependency is this single trade for the whole purchase history of this buyer on this single trade, right? And also for the same seller, right? As a seller, I have many different transactions possibly. Um, this single transaction that we or pair of buyer and seller that we're talking about, how much of total revenue as a seller I'm receiving as a share from this single buyer. So that's kind of the dependency comes from that. So we create a weight for buyer, a weight for seller, and then we um, take the average, and that would be our symmetric weight. So the reason we do this is that we are not focusing too much on a scale. The scale is important, but dependency is even more important, right? In buyer-seller network, the fact that there is a high-weighted link, if we interpret that as not necessarily there is potentially large economic transaction are happening between them, but also they are very dependent in their trade with each other. Right? So that notion of dependency compared to what other they're doing, that makes our interpretation of this relation smoother. Again, you can actually play around with it and just use the weight, or don't use the symmetric notion that I have, or use a directed graph. We have all different possibilities to um, essentially experiment here. And again, I use that weight here and I add the edges, sorry, and then The weight would be just the weight sum, and weight is something that the PageRank algorithm expect to receive, and we define it like that. A strength is just the degree or the number of neighbors. Here, obviously, it's a weighted graph, so the sum of the weight or the transactions that you receive from your immediate neighbors as a buyer or seller. HHI, we define it, we just apply the function that we had on different buyers. So we get the HHI, and then we combine everything in one matrix and then sort it up in different buyers and sellers. So the rest of it would be just simple enough. So let me just calculate and see what we get. Okay, so that's what we get. So we calculated, and what we see that we have um, some, interestingly, in this example, the top broker that had the highest betweenness, that is also the seller that is also the top hop, interestingly. So that is what essentially the notion of a small world or um, high-scaled networks usually gives you, that when we have hubs that more proportionately get most of the transaction, most of the edges, they could be possibly dominating lots of network metrics. So that's what we see that, interestingly, the top broker is also top hub. And then actually I can look up here as well and look up that we have some buyer and seller mix in terms of who is um, um, more between different deals and different transactions. So we have these top brokers, we have these top hubs, and we have some cases when, for example, this seller is relatively high in terms of a hub, but this is not a broker. So it's not that both of them are the same. So intermediating deals are not the same as being central in many deals. And dependency as well. We have different buyers here, that the higher this number is, the more concentrated I am in a limited number of sellers that I'm really relying. And that is, as a buyer, that's a little bit concerning, because if something happened to these sellers, then maybe there's more work on my behalf to find different sellers, different suppliers, um, if I'm too much reliant on a limited number of sellers. So that one interpretation, depending context, we could have other interpretation as well. So let's now look at the visualization, the fun part. So visualization here, we're actually visualizing in two different ways. This is a bipartite format and a dynamic format. So very quickly, essentially, if I want to explain, so the main problem is that we have these raw force layouts in the bipartite nature, right? That got mixed, and it kind of became hard to interpret. So we make it soft a little bit, so there is no overlap between buyer and seller. So that's what you get in this visualization. And then we also assign different colors based on the some cutoff to how large the amount of the weight or trades are in each link. And then we create some more dynamic version as well. So this is the render flow HTML dynamic, which is that more there is some sort of the dynamics is defined by this physics configuration here, and network is the key part that defines that dynamic, more chaotic shape that you saw initially. And this is defined that whether you want be this to be the possibility of dragging, the possibility of zooming, um, physics enabled true. That means you want them to be, there is some dynamics involved. Also the fact that this gravitation and other sort of parameters, some of it are related. The fact that you want them to be non-overlapping, so even if you drag them toward each other, they're gonna move away, and there's some movement involved. And how stabilized you want it to look like. So you could specify in here as well. So that is kind of that flow dynamic. The bipartite nature is more, again, we use the same network format, but as you see here, uh, the fact what makes them bipartite is how we define the position of buyers and sellers, right? We here you see this minus, and we don't have this minus. That's essentially we are using a symmetric um, position where buyers on our left, sellers on our right, but there is some um, randomness which we define in terms of the exact position, but that is what creates that bipartite nature essentially. The rest is the same, but if we make them configuration is much simpler because we don't want any dynamic here. Um, we want them to be fixed in place, but also we want it to be zoom and drag and everything. And also you can add colors, adding labels and other visualizations here, right? So let's um, do this, and then we can look at the um, visualization at the end. Let me go over one more thing. The buyer similarity is what you see here. Is essentially we are going to do this. We're gonna create um, the cosine, which is that's the formula for the cosine similarity essentially. And again, in the companion theoretical video, I explained that. And that is the big thing that we're adding in this video, right? So usually the similarity or clustering, you could do it in non-network context, you could do it based on different features, right? So you have two different options to define that similarity. One is based on the network itself, which is this one is based on how similar your choice of partners have been to others. This is based on this part is based on how similar you are as a buyer in terms of region, industry, and size. So we define that similarity in CTX, and S spend is based on the network spending. This is based on the other features, right? So this is that kind of closer to the clustering notion in outside network. And then we have this alpha, which actually it is defined in config JSON that we had, that gives us this weight, right? How much you want your similarity based on the network and based on the other features. So in this case, I want to actually just focus on the network itself. I don't care about other features. That's why I make it to be 0. So 0 on this one, every weight on the network itself. And then in the final visualization, you can have a cutoff um, in terms of what is the cutoff you want to define to, if the similarity matrix is bigger than that cutoff, then we have a link, right? So that's something that, again, it's in the JSON file, but that's something you can play with it and see what makes sense with your context. So let me now add this as well. So that would be different buyer pairs, and we did their different similarities, right? One more thing, then we can actually apply the same idea. And again, I explained about the interpretation of PageRank and betweenness in a buyer-buyer network. But same thing, you can repeat the same idea and calculate um, on a different network, but same idea, betweenness and PageRank, although the intuition will be and the meaning will be much different because the meaning of having a link is different in this network. And lastly, we're going to do the community detection based on the similarity in the buyer network that we've done. And community detection, again, the theory part of it is in the companion video part 1. We use modular based community detection with some greedy algorithm here. Greedy modularity community is the one that we're going to use. That's one of the common ones. And essentially this part, let me explain. So I kind of had a challenge that I didn't know the meaning of this community, the different colors that you see in the early in the video. So I wanted to add some labels in terms of what are the features of different communities, right? What is the biggest repeat in terms of the industry? What is their spending mix? Is there any similarity? What's the reason we see these communities, right? So I'm doing that. So getting over those features to define what are the key features on those communities, and we are making them as a label in the visualization for the buyer part. So again, if you run this, and then that give you essentially the summary buyer information data that you may want to have. And lastly, that is the visualization for the buyer summary similarity network itself, which now we're going to end up looking at the final outputs that we wanted to have in different formats. One last thing, which is the fact that although you can also repeat the same thing with a more extensive data, which was our run 2, which if you do, you should be able to find different network format to your data. So let's have a look at what we created. So this is the bipartite nature, the first visualization on the network itself, right? That is the usual buyer-seller network that you expect to have. And here, as you can see, we add the labels. So we one of the central ones were this seller. So this was the seller that was both the hub with the highest PageRank centrality, but also because this one is had deals with many buyers, and they themselves um, have deals with other part of the network. This is also the buyer or seller or the node with the highest betweenness, that is brokering and connecting different part of the network, interestingly. So again, in bipartite network, these have their own specific definition, which I explained in before. So this is the second layout where you have your dynamic. If I bring it up, you see that kind of interesting chaotic when it starts, and then based on the gravity we define, they slowly gonna stabilize in their own place. When there is not overlap, there is sufficient kind of distance between each other, and we can drag and drop and see, okay, where is that um, biggest. I think there you go. That is our supplier 29 in this format. This is essentially looking from a different angle, right? That hop. Now let's look at the similarity. The similarity, this is what we had before. So that's essentially what you have in the similarity piece, where this is one community, this is another community, and each of them based on the sort of trading partners that they have. Now, if you run your data with a much larger number of nodes and edges, buyers and sellers, then you're gonna have something as chaotic as this, right? This is a very large network where nicely we can visualize what's going on. You can kind of navigate, zoom in a little bit slower to see what's going on. So that is the buyer similarity in a much larger network. Right? And lastly, I ran the second run of the data on a much larger data, and you see this is the flow network where you have much larger with the dynamic. So there are different visualization possible with a set of data and functions that we define. Hopefully this was useful. What we did in this video, focusing on visualization and defining a set of network metrics. The purpose was to focus how we can look at different perspective of the data transaction data. And buyer-seller networks are one of the common and interesting networks to look at. Hopefully this has been useful to you. See you in future videos.